Welcome to Module 14 of Mechanics of Materials, Part 1. Today's learning outcomes are to go back. We had talked about shear stress earlier in the course. We're going to go back and talk about it in more detail now. And we're going to review 3D stress at a point, along with that sign convention we discussed earlier. And we're going to define and discuss something called 2D pure shear, two-dimensional pure shear. And so recall, for Mechanics of Materials, we start with an engineering structure, and we apply external loads to it. We look at the internal forces or moments that's taking place in the member itself to calculate stresses and strains and evaluate the structural performance. And so that engineering structure may be a bridge, it may be a mechanical device, it can be any kind of engineering structure. And we may have connections in it which are going to be subjected to shear. And so we have here a bolt, and then it's being pulled. This is called single shear in one direction and another direction, and then we have double shear where we're pulling on it here in one direction, here in the other direction, and down here in the left direction. And so this is a picture of a shear bolt that's being subjected to these shear forces. And so here it is again. And so we're putting forces perpendicular to the length of the cross section. I have an example of a shear bolt here. And so these shear bolts are important in design. I used to work on my grandfather's farm when I was younger as a teenager, and we had machinery that worked off of PTO, power takeoff shafts. And so you would have shear bolts designed into the power takeoff so that it would be designed to shear off at a certain amount of shear stress, because that would protect other parts in the piece of machinery, like a baler or something like that, a hay baler. So we use shear bolts for that kind of application. And so when we do a cross section, we see that we have stresses along the face, parallel to the face. We assume that they're uniformly distributed like we did before. The total force is equal to V and counteracts the external force being applied. Shear stress was defined again as the force per unit area parallel to the cut surface, and it was given the symbol tau. And so tau is equal to the shear force V over the cross-sectional area. And so let's go back and review a three-dimensional state of stress at a point. Here again I show it with the positive sign convention, which means positive stress on the positive face for the x direction. On the positive x face in the positive y direction, we have tau xy, etc. And here is our piece or our part subjected to shear stresses. And for two-dimensional shear, or 2D, what we call 2D pure shear, we take away all the normal stresses, and we take away all the out-of-plane stresses. And all we're left with is the tau xy, tau yx on the positive x and negative x face, and the positive y and the positive or negative y face. And by equilibrium, if I am to sum moments about any point on this block, let's go ahead and sum moments down in this corner so the forces due to these stresses would cancel out. I'd get tau yx times its cross-sectionality times its moment arm, which would be, say, a distance d in this direction, and it would be clockwise. And then I get a counterclockwise moment, tau xy times its cross-sectional area times its moment arm, which would also be d for a square cross-section. And so by equilibrium, we see that tau xy is equal to tau yx, or we're just going to call it tau for the case of two-dimensional pure shear. And we'll pick up from that point next module.